Can everybody hear me up there? Good? All right. So we're continuing with our discussion of Turing machines. And we said a Turing machine is simply a finite automata with a tape. It has all the features of a finite automata, a set of states, transition function, initial state, final states. But it has an infinite tape that it can use as a scratch memory to read and write from, aside from reading the input from it. So as it churns along, it can change states like a finite automata, but also look at the read-write head tape location that the read-write head is pointing at this moment. And the state transition function can depend on that as well as on the state that it's in and the character that it's seeing and so on. So it's a very simple model of computation, but the simplicity is deceptive because it's the most powerful one we've ever invented, and we can't think of any ways to increase its power. It can do everything that we think is doable computationally using machines, using computations, using algorithms. So in the book, it's coming from chapter 3.2, so you should refer to the book on all that. And give an example of a Turing machine to recognize a couple of simple languages. You should look at more examples in the book. There will be more examples in the homework even. But we asked whether we can increase the power of Turing machines using various so-called enhancements. If you use, for example, a larger alphabet, it turns out that that's not going to make any difference because you can encode the larger alphabet with a smaller alphabet. It's essentially what all computers do, right? Using the Unicode character set or EBCDIC or ASCII character set, you can encode large character sets using only 2 characters, zeros and ones. So larger alphabets don't really make a difference in terms of recognition power of languages. And double-sided infinite tape, we can take the infinite tape that's double-sided and simulate it with a single-sided infinite tape. The way to do that is simply dovetailing. Basically, you conjoin or interlace the 2 halves of the infinite tape together, giving you a single one-sided infinite tape. And using that single-sided infinite tape, you can do whatever a double-sided infinite tape does. So again, having a tape that's infinite in both directions doesn't buy you any extra superpower, just convenience. Okay. And multiple heads can be addressed by simply encoding the different heads using a single head by creating sort of uppercase characters or additional characters that denote the old character on the tape, plus the fact that the particular head is on that tape square as well. So you can encode the head locations kind of virtually on top of the characters that's already on the tape by using capital characters or some other characters or some other marks. You have a wide choice of options of how to implement this. Once you do that, a single-headed machine can do whatever a multi-headed machine can do as well, so that doesn't buy you any extra power. And of course, keep in mind that in each case, one of these enhancements, you have to modify the transition function appropriately so it does the right thing. In the case of here, for example, you have to scan the entire portion of the tape that you've touched so far, and it's always a finite portion. You never touch an infinity of squares on a tape because you never compute to infinity, you always compute to a finite number of steps at every point in the computation. Whenever you touch a character on the tape, basically, to simulate multiple heads, you have to go and see where the heads are virtually by seeing where the capital characters do the right things for each virtual head, move it left, right, change a character underneath its location, and then do that for every single step of the multi-headed machine. So it's tedious, yes, it's not convenient, sure, but it works, and it works pretty straightforwardly and mechanically and systematically, and so many heads here are not better than one. For finite automata, remember they were. Multiple heads were better than 1. 2 heads were better than 1. 3 heads were better than 2 even. For PDAs, same thing. Multiple heads gave you an advantage. They gave you a superpower. It gave you the ability to do things that you couldn't do before. For example, a 2-headed push-down automata can recognize 0 to the n, 1 to the n, 2 to the n, but a single-headed push-down automata could not do that. In fact, even a 2-headed finite automata can recognize this non-context-free language, 0 to the n, 1 to the n, 2 to the n. So multiple heads were a tremendous superpower for finite automata and for PDAs, but not for Turing machines. Next enhancement we looked at is multiple tapes. What if you had many tapes? Is that better? Is that buy you the option of recognizing new languages that you couldn't recognize before? Short answer, no, because you can, again, dovetail or interlace the tapes together, track everything like you would expect, and simulate the 3 tapes with a single tape. If you had 17 tapes, you do the same thing, just 17 way interlaced single tape of 17 different original tapes. So multiple tapes don't buy you any extra power. And next enhancement we looked at is multi-dimensional tape, or in this example, 2-dimensional tape. You can do the same thing. You can take the different rows and interlace them together, but this time you don't even have to zip them together one tape square at a time. You can basically write each block of the tape one after the other. Make sure you separate them with $signs so you know where one begins and one ends, and you're good. And you don't have to store an entire infinite row in any one of those portions, because in each row, the rest of the row beyond a certain finite number of squares is all blank. So you don't need to store an infinite number of blanks. They're implicitly there, and you don't need to waste an infinity of squares to store an infinity of blanks. Right? Just like when you say the number 3. You don't say 3.0000000 and you keep going forever just to convey the number 3. If you just say 3 or 3.0, it's implicit that the rest are zeros. And you don't have to say that or store that or worry about that. And this is called row major order. That's how compilers implement arrays, actually. And non-determinism is a bit trickier, but that too doesn't increase the power of Turing machines. By the way, any questions about everything we covered so far, which is a quick summary of what we did the last lecture? So non-determinism, you can have choices of next steps, right? And just like non-determinism in finite automata or non-determinism in push-down automata, the computation bifurcates, and you have a computation tree, not just a computation sequence of states, but a computation tree of states. And as long as you arrive at an accepting state on some path, on some branch of the tree, the whole thing is said to be accepting. So it's a very similar definition, in fact, identical definition to that of finite automata non-determinism or push-down automata non-determinism. So Turing machine non-determinism, same thing. As long as there's a way to win, you win. You don't have to worry about dead ends and non-accepts and so on dead paths. But as long as there's a way to success, you're good. So this is like the venture capital model of computation, right? Venture capitalists, they fund many companies. As long as one succeeds, becomes Google or Facebook or Yahoo or whatever. Yahoo is probably not a good example because it didn't do too well. But as long as one succeeds, the rest fail, that's okay. You're still good. So non-determinism, one branch of the computation can do one thing and another branch can do another thing. So for example, if in one branch you went to the right and the other branch you went to the left, the blue branch you went to the left and overwrote that with a 1. So again, this is where you start. And non-deterministically, on one branch you go to the right and don't do anything to that one. On the other branch, you start here and you go to the left. And when you go to the left, you overwrite that 0 with a 1, and then you go to the left. End up in these 2 different branches of the computation, and the tape looks very different. Each branch has its own tape. It's not the same tape that they're all using, obviously, same as PDAs. So how do you keep track of all these branches of non-determinism as the computation proceeds? Question? Oh, good. Well, what do you say then?
Create a copy with a new head.
Yeah. So basically, you create a copy of each branch on your single tape simulator. So copy this and copy that both on your single tape. And you have to mark in each copy where the head is by, and we already know how to do that because now we can have 2 heads, and 2 heads really are just capital characters or marked characters, bigger alphabet, which we know already is not a superpower. And once you do that, keep track of all these multiple threads of the computation, keep them separate with special marks like $signs. Again, use a larger alphabet if you have to. If you don't like $signs, use euro signs or yen signs or shekel signs or whatever. The point is you can keep track of all these multiple threads and then simulate them in parallel, round-robining between them. You don't take one thread and simulate that ad infinitum because that can go to infinity and fail or never stop even, where the other branches can stop and succeed very quickly, and you want to know that too. So you need to do it in parallel. By parallel, all we mean is keep simulating each branch of the computation by 1 step in lockstep in turn. So each branch gets 1 step forward, and then all of them get another step forward in turn respectively, and so on and so on. Just make sure you do it in parallel. What if this branch now becomes two other branches? The blue branch becomes two other branches. What do you do then? It's not a trick question. It's easy, yeah. Yeah, just copy that branch again right after that. Now you have one more branch beyond that, or two more branches beyond that, and you just keep piling them up on the tape and make sure you simulate all of them at every single phase of the computation. So no branch gets starved for CPU cycles, quote unquote. How many get all this? Okay, any questions? So it's parallel simulation, basically, showing that non-determinism doesn't buy you any extra power. Now, it's not a trivial observation, because remember, for finite automata, non-determinism didn't buy you any extra power. In 2 words, what was the proof technique there? That for finite automata, non-determinism didn't buy you any extra superpower. 2 words? Take a wild guess. Yeah. Cross product. It's actually generalization of the cross product. So cross product is close, but let's kind of nail it down tighter. Yeah. Power set, which cross product is a special case of power set construction. Okay. The point is it was parallel simulation still. For PDAs, non-determinism was a superpower. For PDAs, non-deterministic push-down automata could do more than deterministic ones can. For example, WWR palindromes are recognizable by a non-deterministic push-down automata, but not by any deterministic one. So finite automata, non-determinism was not a superpower. PDAs, it was a superpower. And Turing machines, it's not a superpower yet again. So it flip-flopped twice, this property, as we went up the Chomsky hierarchy from regular languages to context-free languages, now to decidable and recognizable languages, Turing machine languages. Okay, any questions about that? So it's a general technique. We've seen this technique before, parallel simulation. Now we're applying it to Turing machines, showing that non-determinism doesn't buy you anything extra. Now what about, you have combinations. We showed each property or each enhancement separately, but what if you have combinations of enhancements? So let's say you have a Turing machine that's really complicated. It has a 2-dimensional tape with a certain alphabet, on which tape you have 3 different heads. And separately, you have another tape on top of that, and that tape is two-way infinite, and that has yet another alphabet altogether. It happens to be the Greek alphabet for that tape. You can choose your alphabets when you design machines. And not only that, it has 2 heads on this tape, and it's non-deterministic on top of all of that. Right? So what about this complicated Turing machine with all these enhancements going on all at the same time? Is that any super-powered machine, or is there a 1-tape, 1-head, deterministic Turing machine that does the same job that this one does? What do you think? How many say this has some superpower in combination? How many say same thing? Oh, good. I'm proud of you, my Padawans. The force is strong in you. Okay, good. Anybody want to explain why? Why is this machine no more powerful than a single-head, single-tape, deterministic Turing machine of an ordinary kind? Yeah?
You can collapse the enhancements one by one. So maybe you start by collapsing that 2-dimensional thing into a 1-dimensional one, then you collapse the two-way infinite tape into a 1-way infinite tape, then you collapse the 2 tapes together, then you represent all the heads.
Exactly. So basically, you can, these transformations, if you will, or enhancements, these transformations, how we gotten rid of the enhancements, they all do what with each other? They compose. They can be composed together, right? And not only they compose, they can be composed in any way you would like. So they're commutative as well as compose with one another very nicely. So first take this machine, and like I said, take this 2-dimensional tape and collapse it to a 1-dimensional tape, keep the 3 heads there. Next, get rid of the 3 heads on this tape by doing this capital letter business that we talked about earlier a few slides ago. Next, take this 2-dimensional tape, 2-directional double infinite tape down here, make it into a single 1-dimensional single infinite tape by zipping it together like this, dovetailing, and get rid of this 2-way infinite tape into a 1-way infinite. Then merge this tape with that collapsed tape, dovetailing again, get rid of the extra heads if you must, increase the alphabet size to include all these characters and whatever other characters you need to mark the tape for all the different heads. And then finally the big one, get rid of the non-determinism by doing this, what we just did on a previous slide. And you'll end up with a one tape, one directional infinite, one head deterministic Turing machine that does the exact same thing that this complicated one does. No big deal. So these enhancements compose. They can be composed in any order you like. And you get the same thing. By the way, what does this word here on this tape say in Greek? Anybody know Greek? Or at least enough to read that word? It's a trivial, quiz. Plato, it says Plato in Greek. So good, some of you have a classical education. Or maybe you just belong to enough frats that you recognize all the letters. Either way, you got it. You're right. So any questions about any of this? Straightforward. So let me ask you a question, a subtle question. So these transformations compose. If you can compose them one way and compose them a separate way, let's say you collapse this tape first into a one-dimensional tape and then combine it with this tape and then gotten rid of the non-determinism. Or if you've gotten rid of the non-determinism first and then collapse this tape next as another transformation, a second transformation, then you collapse this two-directional infinite tape into a one-directional infinite tape and then combine the two tapes, and then you've gotten rid of the heads, or multiple heads, all at the end. These two different processes where the order of the collapsing or the compositions was different. Will you end up with the exact same Turing machine at the end in both times? How many say yes? How many say no? There'll be different machines. Don't want to be presumptuous. How many understood what I just asked? All right, not enough. Let me ask again. So we're converting this non-deterministic, double-tape, multi-head, multi-alphabet, two-dimensional taped, bidirectional, infinite machine that's got all these enhancements at the same time. We're converting it to a single tape, single head, deterministic machine. It's only one-way infinite on the tape. Now, we have a choice of in which order to apply these collapses or transformations, right? How to get rid of the enhancements like we showed on the previous 5 or 6 slides. So my question is this. If you apply these enhancement collapses or enhancement transformations and get rid of these enhancements one at a time in one order, and if you apply them in another order separately, will you get the exact same machine at the end, exact same Turing machine at the end, regardless of which order you apply these transformations? What do you say?
I think back to the centrifuge and how these operations are non-destructive in a certain way. So we should be able to preserve any of the original properties no matter how we do the steps and the order we do them. So we should have something functionally equivalent at the end.
It's functionally equivalent, but is it the same Turing machine? Does it have the same set of states, the same transition function? What do you say?
I say no, because by definition, Turing machines can represent all other Turing machines, so there is an infinite number of Turing machines that do the same thing but aren't the same machine.
Yeah. So he's saying there's a lot of Turing machines that do the same thing but aren't the same machine. Just like there's a lot of programs that print out prime numbers, but they're not the same program. So if I ask all of you to write a prime number generator, the program just prints out prime numbers without stopping, and you all work independently, chances are no two programs will be exactly identically alike character for character. How many get that? Unless you copied from one another, but that's a whole different story. Or by some fluke or chance, maybe one or two pairs will be identical, but you'll probably pick different variable names, different spacings, different tabbing, different ways of looping, and so on and so on. Same with Turing machines. In fact, for every algorithm, there's an infinite number of other algorithms that all do the same thing. And the same holds for Turing machines or programs. So prove to me that for every program that does something, there's an infinite number of other programs that are different than the first and all different from each other, that all do the exact same thing, i.e. they have the same input-output behavior. For the same inputs, they all produce the same output. No change on whatever inputs you give them. So how would you prove that? It's easy. That's a hint. It's very easy to do. So it's not a deep question here.
If you have a programming language that doesn't care about white space, you could just add it.
Okay, so for example, you can mess around with white spaces and add more spaces. Let's say we don't even worry about white spaces. As long as they're white space equivalent, all white spaces are equivalent to any other combination of white spaces. So it's not even that issue, although he's absolutely correct. Or you can throw in comments, for example, and it'll be technically a different program because it has different comments. But let's throw in actual executable statements and not white spaces and not comments and still prove this. I just wanted you to see how ubiquitous this phenomena is. It's not about white spaces even. Yeah. Okay, so we're trying to come up with programs that do the same thing, but if you use diagonalization, you'll get something different than the previous set. But I appreciate the try. What else could you do? Let's have other people. I don't want to call on people and put you on the spot, but if the same three people keep impressing me, which you are, in fact, everybody who speaks up is impressing me without even caring what they say because it takes courage to speak up. To feel the rush, the adrenaline, speaking in front of a crowd. I mean, I do this all the time, but I'm used to it. But I want people to speak up, get involved, say stuff. Yeah, what do you say?
You just write a bunch of if statements that never execute, sort of get false, don't put anything underneath it.
Sure. Have a bunch of statements that are kind of isolated and never get invoked or executed like an extra subroutine. Let's take it even a step further. Let's add statements that do get executed. So it's not even about dead code that never gets reached, although that's correct. And that's white space is correct too. Comments are correct too. What do you say?
If you use any value at all, you can store it to a variable, and then you can store that variable to another variable.
Sure. Add an extra variable that you don't need and copy something else to that variable, but don't use it, or even use it. Square it if you must. Take the square root of it if you have to. But don't get that square root or the square involved in whatever else is going on, and you're doing other things, and it's a different program. What do you say? Sure, do a bunch of no-ops, right? No operations, like instructions that don't matter, right? What else?
This is talking about a tick-based machine, so implement a defragmenting algorithm, which technically makes things faster, but doesn't actually affect it.
Yeah, you can pull all sorts of manipulations on the program. What else? I just wanted to see this phenomena very, very clearly, how ubiquitous that is. For every algorithm, for every function that you can compute, there's an infinite number of ways to compute it, all different in one another. Whether it's a program, a Turing machine, finite automata, yeah. Put a bunch of go-to statements, and where would you be going to? Go to the next statement that doesn't do much. And the go-to can go to the next statement, it's also a go-to, and that can go to find the statement that he would have gone to without the go-tos, for example. Better yet, give him even more general solution. If you want to print out prime numbers and you write a prime number program that prints out primes, give me another program that prints out primes that's a lot more complicated and sophisticated and convoluted and longer than that. That still prints out primes. That's exactly what it does. Yeah. Do any other computation you'd like. So we don't print out primes? Great. First, play 1,000 rounds of tic-tac-toe with itself, and then print out primes. Or solve some chess problems, and then print out primes. Or play a few rounds of World of Warcraft or Second Life or your favorite video game, and then print out primes. And that'll be a very long program. And it'll still do all sorts of crazy things, but it won't affect the input-output behavior. And you can have an arbitrary number of them, an infinite number of them. Is that number countable or uncountable? Just to nail that one down. How many different programs are there for prime number? Countable or uncountable? How many say uncountable? How many say countable? Yes, good. Now we're getting it. Why countable?
You sort them by length.
Yeah, sort them by length, by lexicographic order. That's dovetailing, right? In fact, there's only a countable number of programs altogether, never mind just tic-tac-toe programs, of which tic-tac-toe programs are a tiny subset, infinite subset, but a small subset. So now you're getting it. So I just wanted to make sure you kind of wrap your minds very tightly around this stuff, and you seem to be, so that's great. I'm proud of you. Okay, and that brings us to chapter 4 about decidability, recognizability, and enumerability, and we're about to go into that. So please, dive into chapter 4, page 165 and onwards. And today we'll talk more about these enumerators and deciders at great length. So recognizability versus decidability. What is that about? So a decidable language is one that's accepted by a Turing machine that always halts. You can have a Turing machine, whatever you give it as input, some string, it either accepts and halts or rejects and halts. Like if I ask you, is this number that I give you, is it a prime number? If it's a prime number, you say either yes and stop, or you say no and you stop and assume you're correct in either case. And that's the kind of Turing machine we're talking about here that always halts. You're not allowed to run forever. If I give you a prime number, and if I give you an integer and I say, is it prime, and you just take your time and run forever and never get back to me, at this kind of machine, that's not allowed as a behavior. You must always stop implicitly and always give the right answer after a finite number of steps and never run forever. Yeah?
Does that mean that the halting problem is actually asking whether a particular problem is decidable, and also that there is no algorithm that can figure out whether
So there's no algorithm that decides the halting problem. That's correct. But there is one that recognizes the yes instances, and we're about to discuss that. All right, so a language is said to be Turing decidable or just plain old decidable. Sometimes Turing is mentioned so many times and so many things that sometimes omit his name off of it. So a language is said to be decidable if and only if it's exactly the set of strings accepted by some always halting Turing machine. So such a machine always halts. And if such a machine always halts and it solves your problem is decidable. Okay. Now, here's an example. So let's say all the strings in sigma star are enumerated in the first row here. So A, B, BA, BB, and so on. All the strings in sigma star there in the first row. Let's say the machine on that string halts for the A. And when you feed it an AA, it halts also. For an AAA, it halts. And then it doesn't halt. X means reject. So for all these other strings here enumerated on the second row, where all the red X's are, for those strings, it rejects them. It still explicitly halts, but says, no, I reject that string. So it always halts, but says yes and yes and yes for the green check marks, and says no for all the red X's for these corresponding strings up here for sigma star. In other words, the language of this machine is the string A, the string AA, the string AAA, otherwise known as all the strings that the machine halted on, that accepted and halted. So what's the language of this machine just from staring at this pattern here? What would you guess that the machine is accepting just from this simple set of initial examples? Set of all strings containing A's. In other words, it's accepting A star. So the machine is always halting, though, for every string that you give it, and its language is A star. So that's just an example. And the language, therefore, A star, is a decidable language because it has a Turing machine that always halts. In fact, it's more than that. It's also a regular language in this example. But it doesn't have to be regular. It could be a set of all primes or strings made of all strings of prime length or all strings that have length that's a Fibonacci number or perfect square or a perfect factorial number or whatever. But these are all decidable languages. Okay. So if you have a machine that's allowed some more leeway, though, so now we're going to say you can accept or reject and halt in both cases, but you can also run the option of never stopping. You can also run forever and not stop. So if you run forever and not stop, whatever that is, whatever that behavior is, it's not an accepting behavior. It doesn't accept and says yes. You don't say no, but you don't say yes. And anything other than a yes is automatically a reject. So running forever is an implicit reject, right? It's rejecting by not doing anything useful, just running forever and keep running. Never saying yes, but not saying no either. It's like the cold shoulder kind of treatment of computation, right? Like if you try to reach somebody, text them or call them, and they don't get back to you, and you text them, ask them, do you want to do this or go out for there, and they don't reply and they don't reply, that's not a yes, right, in real life. And that's not a yes in computations either. It's not an explicit no, it's an implicit no. But when you give that machine the option of kind of cold shouldering you and never getting back to you, that's not a yes. So we say that's an implicit rejection. Not an explicit rejection, but an implicit rejection, because it's not a yes, it must be a no. And that string is not in the language. It causes the machine to behave this way. All right, so language is said to be recognizable if and only if it's exactly the set of strings that are accepted by a machine of this type that's allowed to run forever sometimes. So it's allowed the option of implicit rejection by running forever as opposed to just saying no and stopping. Okay. So as an example, here's the similar example to before. Here's the set of all strings in sigma star up here. And let's say for A, it accepts and says yes. For an AA, it accepts and says yes. For a B, it stops and says no explicitly. But for an AB, it runs forever. And for a BB, it runs forever also. So whenever you see this infinity symbol here, it means it runs forever. So, but they're all rejections. The X's are explicit no rejections. But the infinite symbols are implicit run forever type of passive-aggressive, cold shouldery kind of rejection. And that's okay. It's still rejections nevertheless. And the language is still A star, right, from this example. So that means that A star is a recognizable language as opposed to a decidable language. Right? So this definition parallels the one we saw in the previous slide right there. So if you always halt whether you accept or reject, the language is decidable. But if you're allowed to run forever, now the language is recognizable. And we're about to prove a series of theorems on these properties. They're very fundamental, very important foundational properties. Decidability and recognizability. Okay? Any questions so far? Because the definitions seem innocent enough. There's only a couple of them. The only difference is you're allowed to run forever, and that's equivalent to rejecting. Right? So what can be such a big deal about that? And you'll see in a minute what big a difference that makes, actually. All right, so again, I remind you that decidable means Turing decidable, recognizable means Turing recognizable. So the first theorem, that's an easy one. Every decidable language is also recognizable. How would you prove that? And hint, it's easy. This one is not a deep theorem. Let's get more people participating. How would you prove that if a language is decidable, it's also recognizable? And I'm color coding it. Decidable is in green, recognizable is in red, to match the previous two slides with the definitions and verbiage on there. So again, decidable means you always halt and tell whether it's in or out the language. Recognizable is you can halt and say whether it's in or out, but you're also allowed to run forever, and that's implicitly a no. Yeah.
Use the same Turing machine?
Yeah, exactly the same thing. So if you have a machine that always halts, it's also a machine of the other type that has the option of not halting when it wants to reject, but doesn't exercise that option. How many get that? That's it. So one is a type of the other. So it's completely subsumed. One definition is completely subsumed by the other definition. If you have the option of running forever, doesn't mean you need to exercise that option. Right? I mean, you all have the option of giving all your cash to charity. You do. You have that option. It doesn't mean you should all rush and do that, although you could. So that's what an option means, right? You have the ability but not the duty to do something. Okay? All right, so we just proved this first theorem. Any questions about that? So this just drives home the point that one definition is a subset of the other, really. Okay, next theorem. Some recognizable languages are not decidable. So just so you don't get this crazy idea that they're both the same, they're not. So prove that to me. Halting problem. How many see halting problem is one of those? About half the class. All right. Somebody explain what he means by halting problem. He's right. What does he mean? Let's expand that concise two-word answer to a full sentence or two. Let's get more people participating. Give a chance to other people first. I could start calling on people right down the row. Do you want me to try that and see how awkward that is? It'll be awkward for me too, but if nobody participates, I can do that. So somebody wants to answer this question about why is the halting problem recognizable but not decidable? Okay, got the same two people. All right. Yeah. For decidable, it has to always halt and say yes or no. So it's not decidable because we already proved that there's no algorithm that always says yes or no and decides the halting problem. Why is it recognizable? What's that? Yeah, so in one word, try to say one word why the halting problem is recognizable. Simulation, bingo, we have a winner. Okay. Anybody want to explain that answer? Why is she saying simulation if she's right?
Because if you just run the program, you can see, hey, if I halt.
Yeah, run the program. If the program halts, you'll know it because you'll halt with it, you being the simulator of that program, you being the compiler that's running that program. If that program doesn't halt, it runs forever, your simulation, your compiler will run forever too. But that's okay. That's an implicit reject now because you have a machine that can kind of cold shouldery say no by running forever. That's equivalent to a no. And it'd be right also. So only the halting programs represented as strings will be accepted by this algorithm that's a simulation or a simulator or a compiler, if you will. How many get this? Okay, good. We're getting deeper and deeper into these theorems. Soon it won't be obvious at all. So the halting problem is recognizable but not decidable. Another way of saying it, decidability is a special case of recognizability. That's what this first theorem says. Okay. So in some sense, it's easier to recognize than to decide. And the halting problem is a good example of that. You can easily recognize halting programs when you see them. But you can't recognize the non-halting programs, so you can't decide yes or no explicitly halting programs from non-halting programs. Okay. So let's define a couple other things. An enumerator is a Turing machine or an algorithm or a program that basically spits out all the strings in the language. And it can run forever because it could be an infinite number of strings. So it just spits out string 1, string 2, string 3, and so on. And you can put them, separate them by $signs however you want on the tape. Allocate a special piece of the tape where all these strings will be listed out, all of them. So the machine never stops if the language is infinite. But that's an enumerator. It's like the enumerator for prime numbers. Print out all prime numbers and nothing but primes. Go. So the program will start churning out prime numbers and never stop. But every prime number must eventually be listed. And no number that's listed can be non-prime or composite. Okay, so that's what's an enumerator, sort of the natural thing, right? Now, the order of the enumeration must be arbitrary. In the case of primes, it's easy to enumerate them in lexicographic order, in fact, in numeric order. 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. These are prime numbers listed in increasing order. But you didn't have to do that. An enumerator can go 5, 23, 2, 11, 3, 29. That's also an enumerator for primes, just not in order. But it must too have the property that every prime must eventually be listed, and it should never list a composite number. So one has the extra feature that it spits them out in order. The other one spits them out in some random order or arbitrary order, but it's still an enumerator nevertheless. So enumerator doesn't necessarily mean in order. It means you spit them all out eventually. Okay. So we're about to prove two theorems here. If a language is decidable, it can be enumerated in lexicographic order or increasing order of some kind. And conversely, if a language can be enumerated in lexicographic order, it's also decidable. So it's an if and only if. So decidability is equivalent, by these two theorems, to the ability to enumerate them in lexicographic order. So how do you prove these two theorems? And once we prove them, we have a complete characterization of decidability in terms of enumeration. So a decider always says yes or no. You give it some string and it says yes or no. Always in finite time, always halts, always gives you the right answer. We already know that. An enumerator just spits out the strings, W1, W2, W3. What is the input to a numerator? It doesn't matter. It's ignoring its input. What's the input to a prime number program? It doesn't matter. You can feed it something, but it ignores it and instead prints out primes. It's oblivious to its own input. Everything has got an input, right? Even if it's the empty file or the implicitly no input or epsilon string or whatever. So that's why I'm saying that the input here is kind of a dotted arrow because it doesn't matter what it is. The input to a decider certainly matters. It's what I ask you to decide, yes or no on, whether it's a member of the language or a non-member of the language, okay? Whether it's in or out of the language. And the answer is always yes or no, always halt, always tell me the answer, always be correct. So that's the difference between a decider and a enumerator. Okay, so if a language is decidable, how can you build an enumerator in lexicographic order from the decider? So we have a decider for it, but we need to build an enumerator from the decider by using the decider as a black box subroutine. How would you do that? How would you build an enumerator in lexicographic order from a decider if I give you a subroutine for the decider? And again, let's try to get other people involved here. Same 5 people keep impressing me, and I appreciate that. But what do you say?
You can enumerate through all of sigma star and feed it through the decider as a filter.
Sure. So you can enumerate all of sigma star. How hard is that? It's just a loop, right? Form all of sigma star from small to large, string size. So if sigma star is A and B, form A, then B, then AA, then AB, then BA, then BB, then AAA, and so on and so on. All of sigma star will be spat out of this loop. And for each one of those, run the decider on each of one of those strings. So run the decider on A, then run it on B, then run it, and whenever the decider says yes, spit it out, print it out. If it says no, keep going to the next one, and the next one after that. Eventually, you will enumerate all strings in the language in order, in lexicographic order, by size. How many can see that? But simple algorithm, right? To get an enumerator from a decider, put the decider in a loop. That's it. Run it on everything in sigma star, one at a time. You don't even have to do anything fancy like parallelize or worry about anything running forever because the decider always holds. So we just proved the first theorem, that if a language is decidable, it can be enumerated in lexicographic order. Why? Put the decider in a loop. Run it on everything in sigma star, one at a time. That's the proof. Questions about that? Yeah.
When you say put the decider in the loop, do you mean, what would the decider do exactly? I missed that.
Okay, so the decider takes a string and tells you whether it's in the language or not by saying yes or no, always in finite time, always be correct. So have a loop outside the decider. The decider is a subroutine now. Run the loop on sigma star. In other words, generate sigma star from the loop. Generate all possible strings, right? A, B, AA, AB, BA, BB, AAA, AAB, AA, whatever, all strings in sigma star. For each one of those, call the decider on that string inside the loop. Wait for the decider to tell yes or no. The decider says yes, print out that string. So for example, so I'm glad you asked that question. Let's anchor it in reality. How can you build a prime number enumerator from a prime number decider? I give you a function that you give me you feed it a number, it tells you if it's prime or not. But I don't want to know if a number is prime or not for a particular number. I want a list of all primes. How do you build a prime lister from a prime decider? Yeah. Yeah, say for, I goes from 1 to infinity. Put the primality tester, call it on I for each I in the loop. If it says yes, it's prime, print out that number. If print out I. If it says no, don't print out I, go to I plus 1. Try it again, repeatedly. Right? So that's how you build a prime number enumerator from a prime number decider. How many get that? So does that make sense? Yeah, so you can do that in general for any decider, not just for primes. Is a number a perfect square? Is a number a Fibonacci number? Is a number even or odd? Is a number perfect or not? A perfect number is a sum of all of its divisors, by the way, like 6 or 28 or 496. I just happen to know that. But that's how you build an enumerator from a decider. So we just proved theorem number 1. Okay. More questions about this? All right. Let's move to the second theorem. If a language could be enumerated in lexicographic order, if there's an enumerator for it as a subroutine, black box subroutine, that just spits out strings in that language, from it you can build a decider. That's a bit more subtle. Not tremendously, just a little bit different. How do you build a decider from an enumerator? In other words, the other way around. If I give you an enumerator, how do you build a decider from it?
You take your input and then you go through each string printed out by the enumerator, and then if your string appears there, then you accept it. But
Yeah.
as soon as you see a string that's past its lexicographic.
Yeah, exactly. So what he's saying is, to build a decider from an enumerator, you get a string, you want to decide it, you don't know how to decide it, but you got an enumerator. So fire up the enumerator, let it rip. And the enumerator starts printing out strings. If any one of those strings is equal to the one you got, you being the decider, that you were given in the input, say yes and stop. But how do you know to say no? What's the no case? Let's do it for primes again. Let's say you have a subroutine that prints out prime numbers. Just enumerates them in increasing order. How do you come up with a prime number decider now from this prime number enumerator? I give you the number 113. How can you decide if it's prime?
You start with the numbers that are higher than your
Yeah, fire up the prime number enumerator, and when the numbers get to around 113, if 113 is one of those, you could say yes. But if 113 is not one of those, and you get to 117, whatever the next non-prime is, you know you'll never see it again because it's an enumerator in lexicographic order. So once it gets past the number that you need to test for as a decider, you'll know you'll never see it again, and now you can decide no, and you'll be correct. Okay, and that's how you build a decider from an enumerator. So now we flipped it around and proved the other direction. How many get this? So it's not that deep, it's just a little bit more subtle than the first part. But in each case, we did it by a loop, right? We stuck something, let it loop out, and then watched what it's doing, and then we found out what the answer is to our other question. Yeah.
Can't you simplify that argument even further and just say, run the enumerator? The fact that it's able to run without hanging, which is how it produces that lexicographic order, indicates that it must be decidable because the enumerator already has a decider inside it. So if it's able to print out every...
Let's not be too hasty. So first of all, you can't just run the enumerator and that'll be your answer, because you need to decide. You need to say yes or no. An enumerator doesn't say yes or no. An enumerator prints a bunch of strings. A decider must says yes, or it must says no, and that's all it does, and that's all it can do. So you still have to convert something to a yes-no printout to be a decider, right? Secondly, there's a bit of an issue with, you said an enumerator must have a decider in it. That's not completely true. It could have a decider in it, but it may do it some other way without a decider. So for example, if I want to print out prime numbers, I have a very simple program that prints out prime numbers. Print out all numbers. And all the primes will be printed, but non-primes will be printed too, and there's no decider for it right there. Or you can have some other trivial algorithm that somehow gets the job done, but not using a decider explicitly, right? So for example, if I say, print out all strings that have any number of A's and any number of B's in any order that you'd like. You could just print out all of sigma star, and then you'd be right, because that is sigma star. And there's no decider for a string there explicitly. I don't take a string and I say, is it any number of A's and any number of B's in any order? Yes or no? And if it's yes, I will do, there's no decider there per se. So there may be end runs around decision that still gets the job done, right? If I want a clock that's correct, infinite number of times, I can just have a dead clock. It'll still be correct twice a day and therefore an infinite number of times over time. But there's no decision procedure there that checks for the correct time and to see if that thing is right, and it just does the job somehow. So you have to be a little careful, but it's a subtle point. I grant you that. Other questions or issues so far? Okay. So we just proved a pair of theorems. It says a language is decidable if and only if it's enumerated by lexicographic order, and it is an if and only if, so we proved it in both directions. That's a complete characterization of what it means for a language to be decidable in terms of it being enumeratable in lexicographic order. The two are equivalent. The two conditions are the same. They give you the same set of languages. All languages are decidable, and all languages that are enumeratable in lexicographic order is the same class of languages. Okay. Any questions about that? It's not obvious, right? I mean, what does decidability have to do with enumerability in lexicographic order? You know, they seem to be two separate issues or concepts. It turns out they're identical, they coincide in what they define. Okay, we're on a roll, so let's prove two more theorems. This time, we'll prove a language is recognizable if and only if it's enumeratable in some order. I'm not saying which, not necessarily lexicographic this time, some order. And this will be a little harder to prove. Okay, so let's start with the first theorem. So language is recognizable means it can be enumerated in some order by a Turing machine, an algorithm, a piece of code, a program, doesn't matter, it's all equivalent. So why is it if it's recognizable, it could be enumerated? Right? So if you have a recognizer, let me draw a recognizer here. So here's a recognizer, and in comes some string, right? And I can either say yes, or I can say no, or I can say run forever. So now both of these are options. So a recognizer is different than a decider in that it's allowed to run forever. I'm just kind of writing down here on the board what I said a couple slides ago. So back to this theorem. Why is it that if you have a recognizer for it, it could be enumerated in some order? I don't care which. Let's try to get more people involved here. Yeah, what do you say? Yeah, so generate sigma star in the loop, and for each one of those, run the recognizer on each one of those strings. And the one that it says yes on, we're going to print them out. The one that says no on, don't print them out. The ones that it runs forever on, what do you do with those? It's an implicit no, so you can run forever, and you'd be right also, because you wouldn't be saying yes, and you'd be saying no also, and you're still an enumerator. But there's a bit of an issue still. Take it away.
You got to run them in parallel, round robin, so you don't get hung up on any one.
Yeah. Yeah, exactly. You need to run them in parallel, because if you run the first and then the second and then the third and then the fourth in sequence, in serial sequence, what if the first runs forever? You'd be right on that one. But you'll never get to the second that says no or yes even, and you'd be able to report that. You won't be able to report that because you'd be running forever on the first. You'll never get to the second. What do you say? Yeah, and there's many ways to do it. So he named one way. You can say run the first one for, say, one time step. You know, I'm not saying minute per se, because you know, it could be a year, it could be a second. It's all equivalent. So run the first one for one time step, then run the second one for one time step, then run the first one for one more time step, and then the second one for one more time step, and run the third for one time step. Then run the first, the second, the third, and the fourth for one time step. Then run the first, the second, the third, the fourth, and the fifth for one time step. The fifth what? The fifth string in sigma star. So eventually, you'll run every string long enough through the recognizer that if the recognizer eventually says yes, you will see the yes, and you can report that string, and you won't get hung up on the ones that it runs forever on. And that's important in this case. You have to say something about that, otherwise you won't have a complete correct algorithm. So yeah, we're sticking the recognizer in a loop, same as we did for the decider earlier. But this time, sticking the loop doesn't tell the whole story. It's not completely sufficient. You got to stick in the loop, yes, but do a round-robin kind of parallel simulation and give everybody enough time slices that eventually they will stop if they choose to stop, so that the slow ones won't get in the way of the fast ones. And certainly the ones that take infinite amount of time won't block the ones that will eventually terminate. Right? Again, this is kind of the venture capital, kind of model of computation here. You don't want the companies that will struggle for 10 or 20 years to block the ones that will succeed in 2. Right? So you fund them all in parallel and say, oh, everybody go, and the ones that are slowpos or never succeed or fail or struggle for 10 or 20 years like Yahoo did, it won't block the ones that are ready to produce something for you, like a yes in this case. Any question about that? Okay. Next and fourth theorem, if a language is enumeratable by some Turing machine or algorithm, it's also recognizable. So now how do you build a recognizer from an enumerator? And that'll close that loop, right? That will make recognizability and enumerability in any order you'd like equivalent in some arbitrary order, not necessarily lexicographic this time. So again, the last theorem is how do you build a recognizer from an enumerator? So you have a box that's an enumerator right here. And this enumerator just spits out strings. And it spits out strings not necessarily in any order. But you need to build a recognizer from that. What do you do? Yeah.
Could you run each string of sigma star on the iteration of the enumerator so that was producing anything else?
Well, an enumerator just spits out lots and lots of strings. It doesn't run on anything per se. It has no input. So you can't, it's a good try, but you can't run an enumerator on a particular string. It's like prime number generator. What are you running it on? What does it take as an input? Nothing. It just prints out primes. So you have a black box that prints out prime numbers. And from it, you need to recognize if a number is prime or not, and you're allowed to run forever now. That's an option that you have. What do you say? Yeah, so you fire up the enumerator. You need to recognize some string, and you don't know if it's in or out of the language, but you have an enumerator, so you fire up the enumerator, and then you wait to see what it enumerates. String, 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 string. If any one of those is your string that you're trying to recognize, if any one of those strings enumerated by the enumerator is this single string that you're trying to recognize, what do you do? Return yes, right? But if it's not one of those strings, and it's not the next string, it's not the next string, what do you do then? Keep running, keep going, keep waiting on it to finally spit out. And those strings are now not in order. They're enumerated, but not necessarily in lexicographic or increasing order. That's okay, you keep waiting, because now you're a recognizer, you're not a decider. So if these are coming out and your string as a recognizer is not any one of those, you can wait forever. You can afford to do that now because you'll be running forever, sure, but we won't be saying yes erroneously. You won't be wrong by running forever. You'd actually be correct because you're rejecting your string cold shouldery passive-aggressively by not responding, by running forever. And now that's defined as an implicit no. Not an explicit no, but an implicit no. It's certainly not a yes, running forever and not getting back to you. So we just proved the fourth theorem, and we have a complete characterization now of recognizable languages as languages that could be enumerated. Not necessarily in any order, just enumerated. Remember the last two theorems. It was decidable if it could be enumerated in lexicographic order. But it's recognizable if it could just be enumerated in some order, not necessarily lexicographic. So we have two pairs of theorems that beautifully match if and only if-wise and give a complete characterization of decidable languages in terms of languages enumerated in lexicographic order, and gives complete characterization of recognizable languages as language could be enumerated in some order, not necessarily lexicographic. Question? So she's asking a very subtle question. Is there a problem with not saying no? Well, why do we have to run for it? Why can't we just say no? It's a very good question. What's an answer for that in real life? Why don't you want to say no to some offer of some kind, whether it's political, financial, romantic offer? Why don't you want to be very explicit? There's reasons in real life where you don't want to say explicitly no. In case you change your mind, or in case saying no will create all sorts of adverse situations. Maybe you being stalked, or maybe the person is a creep, or maybe it's some salesperson that keeps trying, and if you say yes or no, they'll keep trying anyway because you got some response from you. Maybe it's a troll on the internet, and they posted something to your wall on Facebook, and maybe it's something offensive. But if you say, if you chastise them, guess what will happen next? They'll try even harder to troll you, or you might get a troll storm of a whole bunch of other people. So there's reasons in real life where you don't want to say no explicitly. You just want to say no implicitly by not responding. Sometimes a cold shoulder is the best approach in some situations in life. All right, back to the computational world. Sometimes it's very hard to compute the no. It's onerous. It takes too much time. Sometimes it's worse than that. Sometimes there's no algorithm to compute the no, but there is an algorithm to compute the yeses. And it's easy to do, and there's no adverse consequences of computing the yeses. So you do want to say the yeses explicitly by computing them, but the no's, not only they're hard to compute, sometimes they're impossible to compute. And that's why you choose not to say them explicitly. You choose to say them implicitly by running forever. Give me an example that where it's easy, relatively easy algorithm to compute the yeses, but the no's, there's no algorithm to compute at all. Not even a very slow one, not even a very inefficient algorithm. It's just impossible to compute the no's, but relatively straightforward to compute the yeses. Not hard. We've seen this before. What do you say up there? The halting problem, yeah, exactly. So the halting problem, how do you compute the yeses? The ones that halt. One word? Simulation. How do you compute the no's? Two words? Or one word? How do you compute the no's, the ones that don't halt? We don't. Why? Why don't we? We can't. How do we know we can't? Well, we proved it. It's the halting problem is not decidable or computable algorithmically. That's Turing. That's what Turing did. So the halting problem is one of those things that are recognizable but not decidable. You can compute the yeses by simulation. You can't compute the no's, not because we don't want to, not because we prefer not to. We can't. And not because just we humans can't. It's worse than that. Can an alien race of 1 billion years old, very wise and ancient and omnipotent, can they compute the no's using algorithms, programs, codes, Turing machines? How many say, yeah, they may be able to do it? Who knows? How many say, no, they can't do it either? Yeah, now you get it. They can't do it either. Right? A deity can't do it. It's not doable. Not by algorithms. Maybe if you want to invoke magic or miracles, all bets are off. But not by algorithms. And algorithms is all we got. And don't get me wrong, when I say all we got, it's a lot. We have algorithms to do all sorts of amazing things. Just look at your smartphone, all the millions of apps on it to do all sorts of amazing and wonderful and crazy and impressive things. And algorithms are now beginning to drive us around on the roads with self-driving cars. And they choose what to show you on Amazon based on your history of searches and purchases. And they do all sorts of amazing things. So algorithms can do a lot. Entire operating systems, video games. There's algorithms that take strings of bits from the cloud and project it to your TV screens, those strings of bits, and they're called, they're called movies. Yes, movies. There's an algorithm that presents movies to you in real time, at your leisure. You don't have to go to a theater at a particular time anymore. These are all algorithms. They do a lot of amazing things. So don't underestimate algorithms, but the halting problem is so convoluted, so hard to solve, that there's no algorithm for it, not just for us right now, for anybody ever. That's kind of amazing, actually, that we can prove such a thing. So talking about lexicographic order, there's the alphabetized in lexicographic order. Any questions about any of this? It's subtle, right? And a lot of things will follow from this very quickly. So now we're in a chapter on decidability. Again, this is page 165. I already mentioned at the beginning. So here's an enumerator, like a printer that prints out strings in the language. So this picture here is like this picture here I drew on the board. This is the enumerator I drew. That's where it is right there in the book in terms of a picture. I drew a different picture. It's the same idea. Something that just enumerates strings. Okay. Let's talk more about it. So we said decidability means you never run forever. You must say yes or no, always in finite time. So new theorem, the finite languages are decidable. How many can prove that? Who could prove that? It's easy to prove, so it's a hint. It's a one-sentence proof, really. The finite languages are decidable. How would you prove that? In simulation, in particular, if a language is finite, it's regular. If it's regular, there's a finite automata that always says yes or no. A finite automata never runs forever. How many get that? A finite automata cannot run forever, even if you try, right? It just has to process more and more input strings as it changes states and so on. Even if it's not deterministic, eventually one path will process the input completely. So the regular languages are decidable, and the finite languages are certainly decidable because they're a subset of the regular languages, and finite automata in each case. And the context-free languages are decidable too. What's a decider for a context-free language? A PDA can decide it. Now, if the PDA is non-deterministic and you want to make it deterministic, we know we can't in general do a PDA that's deterministic for an arbitrary context-free language like palindromes. However, a decider doesn't have to be a PDA. A decider can be a Turing machine. And a Turing machine can simulate a PDA, whether it's deterministic or non-deterministic, and always halt and always give the right answer, yes or no. Right? Another word for an algorithm that decides whether a string is part of the context-free language or not is parser. Parser, yeah, part of a compiler. Compiler does this all the time. Remember, we talked about it last lecture, or 2 lectures ago. Right? A parser is something that takes a string and decides whether it's an element of this grammar. What is the grammar in the sense of compilers? The grammar is the syntax of your programming language. What is that string? That string is your program. And the parser determines whether your program is an element of a set of all strings, i.e. all valid programs, syntactically correct programs that are correct in your programming language syntax. All right, just to show you an example of it, why is it so hard to decide and it's easier to recognize? And the holding problem is a great example of that. Let me show you another example. I don't know if we've seen, I've presented this before, but it's worth presenting again. So the set of all cubes, x cubed plus y cubed plus z cubed, sum of all cubes over all integers, right? Is that set infinite? Yeah, because it contains all cubes. If you set y and z to 0, it's still a set of all x cubes, right? But it's a set of all sums of cubes, not just cubes. You know, x and y and z can be 0, minus, or plus, right? All the integers. Is it Turing recognizable? Yes, because you can dovetail through all possible x's and y's and z's by increasing absolute value, and for each one of those, test to see if each one of those is a sum of 3 cubes, and if it is, you know. So you can recognize things of this form. Is it decidable? We don't know to this day. And people have been looking at that for centuries. An algorithm to decide whether a number is actually the sum of 3 cubes. There's no known algorithm to decide that. We don't know that it's not decidable, but we don't know that it's decidable either. It's an open problem. If you solve it, you get an instant PhD in mathematics or probably in computer science too, because it's an algorithm. Let me show you a few examples. So why is it so hard to tell if a number is a sum of 3 cubes? You know, why is that difficult? So if I say if the number is 29 the sum of 3 cubes? How many say yes? 29 is the sum of 3 cubes. How many say no? Yes? Okay, why? Easy. 3, 1, and 1, because 3 cubed is 27, plus 1 is 29. Okay, that was easy. What if I say the number is not 29, but instead it's 30? Is 30 the sum of 3 cubes? And this one I won't ask you to guess, because the answer it is, but this is why. This cube plus that cube plus that cube is 30. And some of them are large negative numbers. I didn't believe it either when I saw it. I plugged it into the Google calculator, and sure enough, it adds up to 30 when you cube these two things and add them up. All right, that's interesting. What about 33? Is 33 the sum of 3 cubes? Again, I won't bother you with that because nobody knows. It's an open question. It's been open for 2,000 years, since Greek times. The Greeks wondered about this too, actually, even though they didn't have computers and programs. So look at this. This question, whether a number is the sum of 3 cubes, went from trivial, 29, you all got that instantly, to add 1 to that, you get 30, to very complicated. You know, imagine how long it would take to compute that this is the answer. You'd have to cycle through all triplets of, you know, in the billions or trillions even, to figure this out. It will take, you know, days or even weeks of CPU time to figure out if 30 is in there. 33, the entire world doesn't know, with, you know, billions of CPUs and cloud computing, and, you know, still nobody knows. Imagine if I gave you an arbitrary number, like a Google -1 or something. So it's just hard to tell, even for a recognizable language, whether it's also decidable. And by the way, Matiashevitz in 1970, in response to Hilbert's 10th problem from 1900, proved that every recognizable set is exactly the positive values of some polynomial. And that was an amazing result in itself. That generalized the heck out of these kind of questions and also showed us why it's so hard. Arbitrary polynomials can do arbitrary computations. Polynomials can simulate arbitrary Turing machines, it turns out, in terms of the positive values that they can take on, multivariable polynomials. We didn't know that. We didn't know that polynomials have this property of computational universality in them until Matiashevitz proved that in 1970. Okay? And next time, we'll start proving all sorts of closure properties of decidable and recognizable languages. Right? We'll prove that the decidable languages are closed under union, intersection, complementation, concatenation, and other things. And on the other hand, the recognizable languages are not closed under certain operations, like complementation. Okay? And we'll pick that up next time. There's an extra week for homework 3. I sent an email. It's due a week after the break. You asked for it, you got it. And the midterm will be the week after that. It will be a take-home, and we'll make an announcement by email. I think we already did make an announcement by email. All right, see you then. Have a safe trip if you're traveling, and enjoy your break.
Quick theoretical question. Language is decidable. That there is no